Okay, so in this video we will solve a problem which again involves rotating coordinate frames, and the goal would be to find velocity and accelerations of a particular point in space, as I will shortly describe the problem. In this problem, there is a disk that is rotating with a constant angular velocity of capital omega, which is also equal to theta dot. The center of the disk is fixed at C. The disk is of radius r, and there is a tether or a thread that is wrapped around the disk. The thread is inextensible, and what is happening is that as the disk is spinning, at the same time the thread can also and is also wrapping or unwrapping. Okay, so the length of the thread is changing as a function of time. So two things happening together: one is the disk spinning at a constant rate, and the thread is wrapping or unwrapping. We have shown a scenario here, an arbitrary scenario, where we see that the disk has at a certain instant the disk has turned by an angle theta. The x and y axis are given by I and j unit vectors, and the disk has turned by an angle theta, and simultaneously the thread has also unwrapped by a certain distance, and that is measured by this angle alpha. So alpha measures the amount by which the thread has unwrapped. Okay, and as the thread unwraps, it always remains taut, and so it always remains tangential to the disk. So we make a couple of points here, and that is L changes as the tether wraps or unwraps, and the tether is always taut. Furthermore, we note that the point Q is the point where the tether is touching this circular disk. It is, in fact, at that point it's tangential to the circular disk. So we mentioned that Q is the point where the tether is tangential to the disk at any given instant. Okay, so that is also given, and then the question is find VP and AP. Right, and now to solve this problem we are going to use a rotating coordinate frame. Our rotating coordinate frame is going to be such that the ER unit vector is always going to be along the length of the tether, so it is always going to be tangential to the circle, and E theta is obviously then going to be perpendicular to ER. So in fact E theta, so in fact ER is going to be making an angle alpha plus theta with the horizontal, because at an arbitrary instant what we have said is, let's say that the disk has turned by an angle theta and the tether has unwrapped by an angle alpha. So CQ is making an angle alpha plus theta with respect to the vertical, which means ER is also making an angle alpha plus theta with respect to the horizontal. And similarly E theta is making alpha plus theta with respect to the vertical. So in fact CQ is parallel to E theta. Okay, so CQ and E theta are parallel to each other. And EZ is then going to be mutually perpendicular to these two, and EZ is it is ER cross E theta is EZ in the cylindrical coordinate frame. So EZ is going to be then like this. It is going to be pointing outwards from the surface of this page, perpendicular to the page. Okay, so with this then the way we will formulate the problem is, we will say that Vp is equal to Vq plus omega cross rho plus rho dot r, where so this is the general equation relating the velocities of 2 points, where the 2 points are moving with respect to each other, and their motion is expressed through a rotating frame. Now here omega represents the net angular velocity of the rotating frame. Rho is the vector going from in this case rho is the vector going from Q towards P, so it's QP. Rho dot r is the velocity of P with respect to Q within this rotating frame, so within this frame. So that is something that needs to be found out. Rho needs to be found out, omega needs to be found out, and of course VQ needs to be found out. Now let us find out what is the angular velocity omega. Now note that the angular velocity omega is the net angular velocity of the rotating frame. So this is our rotating frame. As we have shown here, in this arbitrary instant when the disk has turned by an angle theta and the tether has unwrapped by an angle alpha, we see that the rotating frame has turned from its original horizontal position from alpha by alpha plus theta, and so the angular velocity omega is alpha dot plus theta dot, and its direction, as you can see, because it is turning this way, so its direction is in the positive z direction, so it is alpha dot plus theta dot Ez. Now we know that theta dot is capital omega and it's a constant, so that part is simple. Now we need to find out what alpha dot is. Alpha dot, or the rate of change of the angle alpha, is happening because of the wrapping or unwrapping of the tether. Now let us assume, without any loss of generality, that the tether is unwrapping. In this case you can see that the change in length of this unwrapped portion, let's call that dl, that is going to be equal to r times d alpha, right? Because the lengthening of this tether is happening because of the unwrapping, and the unwrapping and the amount by which the tether gets lengthened is exactly equal to the amount that is unwrapped from the circumference of this disk. So this is the amount that is unwrapped from the circumference of the disk, and this is the change in length. So these two are equal, and therefore if I divide through by dt, then I will get L dot is equal to R times alpha dot, which essentially implies that alpha dot is equal to L dot divided by R. Okay, so therefore we can say that omega is equal to L dot divided by R plus capital omega Ez. Right, so we keep this calculation aside, and we are going to need this vector as we do our velocity calculations, and of course during the acceleration calculations as well. Next, let's also have our calculation for rho available to us. So keep in mind that rho is the vector going from Q towards P. Okay, Q is the reference point, P is the point of interest. We are expressing Vp, okay, with Vq as the reference. So Vp is Vq plus the rest of the terms. So in the rest of the terms we have rho, and rho always points from the reference point or the starting point towards the destination or the point of interest. So you can see that this distance QP is going to be L, and its unit vector is ER. So therefore we say that rho is equal to L ER. Right, now now let us find out rho dot R. So we go back. So rho dot R now is the rate of change of rho. So I'll just write rho equals LER, and therefore rho dot R, this is the rate of change of rho within the rotating reference frame. So here when we consider the change of rho, rate of change of rho within the rotating frame, we don't consider the motion of the rotating frame itself. So a direct derivative should have been L dot ER plus L ER dot, but within the rotating frame it is just L dot ER, sorry. So it is just L dot ER. Okay, so that is rho dot R, because it is a derivative that we are taking within the rotating frame. So we have figured out this vector. Now let us figure out what is the velocity Vq. Vq, that is the velocity of the point Q, is due to two effects. You see, the point Q, the turn in the point Q is because of not only the rotation of the disk, but it is also because of the fact that the tether is unwrapping. So for instance, if the disk was not turning and the tether was only unwrapping, then also the point Q would be moving, because the tether would be unwrapping, so the point of tangent would be changing. On the other hand, if the tether was not unwrapping but the disk was turning, even then Q would change. So you see, it has an effect of both these angular velocities on the velocity of Q. So the best way to find it out is to basically take the position of Q with respect to C and just differentiate it. Okay, we can kind of easily tell that the velocity of the point Q is going to be, due to the rotation of theta, due to theta dot, and due to alpha dot. But for the sake of solving this formally, let us just first give the position of Q with respect to C, which is a fixed point. So, and this is easy to do, and that's why we are going to do it. So RE theta. So going back to our figure, remember we said that CQ is parallel to E theta at all times. CQ is of distance R, and it is in the direction of E theta, and so CQ is RE theta. and so therefore VQ is equal to RE theta dot, because R is not changing. The only thing that is changing over here is E theta, and this is the absolute velocity. This is not within a rotating frame. Okay, so we take this derivative. Now how do we take the derivative of E theta? E theta dot is equal to omega cross E theta, and we do this derivative with the perspective that our right-handed coordinate system is such that ER cross E theta is EZ. So ER cross E theta is equal to EZ. So this is our direction of positive cross products. So E theta dot is then L dot over R plus omega EZ cross E theta. Now EZ cross E theta is going to give me negative ER, because we are going in the opposite direction. So therefore negative L dot divided by R plus capital omega ER. That is our E theta dot. And hence we have VQ to be equal to R times E theta dot, so minus R times L dot over R plus capital omega ER. So that's the velocity of the point VQ. Now next what we'll do is we will plug these different quantities into the velocity equation. So we have, so therefore Vp is equal to, so first you see we have this VQ term, so minus R times L dot over R plus capital omega ER. Then we have omega cross rho, so plus L dot over R plus omega EZ cross rho, and rho is LER. Okay, so let me just write down over here, this is equal to, rho is equal to QP is equal to LER. Okay, so this cross LER, and plus we have rho dot R, so plus rho dot R, that has been calculated as well, so that is L dot ER. Okay, so this is our net expression, and we need to simplify this a little bit more. So we have minus R times L dot over R plus omega ER, plus now we need to carry out this cross product. EZ cross ER is E theta, so we will have L times L dot over R plus capital omega E theta plus L dot ER. Okay, so now we can combine these two ER terms together, and when we do the combination we see that here we have a negative L dot and here we have a positive L dot, so essentially that cancels. So what we have is negative R capital omega ER plus L times L dot over R plus capital omega E theta. So that's our VP, the velocity of the point P. So we have the first result. Now the second result that we are looking for is the acceleration, and so we will develop the acceleration equation. So in order to do that, first let us write the 5-term acceleration expression of the point P, again with respect to the point Q. So AP is going to be equal to AQ plus omega dot cross rho plus omega cross rho plus 2 omega cross rho dot r plus rho double dot r. So a couple of things to keep in mind here. Rho double dot r is the acceleration of P with respect to Q within this rotating frame. So as the frame rotates, what is the acceleration of P as perceived by Q? That is what rho double dot r is. Rho dot r is the corresponding velocity which we have already calculated. We have this, so we need to calculate this vector. We have this one, we have omega, we have rho, we need to find rho dot, omega dot, sorry, and we need to find AQ. So in order to find AQ, what we are going to do is we are just going to take the value of or the expression of VQ and differentiate it. So let me just say that AQ is going to be d dt of VQ. So we are going to take a total derivative, because this is not a differentiation within a rotating frame, rather it's a differentiation, it is the total differentiation. So as you can see here, this is the expression for VQ, and I'm going to differentiate this with respect to time. So we have a little shortage of space here, but I'll try to manage. Let me just keep the diagram in view as much as possible. So and this is actually the expression for VQ. So I'm going to differentiate this with respect to time. So first I'm going to differentiate this quantity, and here r is a constant, capital omega is a constant. The only thing that is changing is L dot. So we have negative L double dot ER negative R times L dot over R plus capital omega ER dot, right? And we need to find out what ER dot is. Now we already know that ER dot is omega cross ER. So this is going to be, so I'll just go ahead with my calculations. So this is going to be negative L double dot ER minus R times L dot over R plus omega. ER dot is omega cross ER, so that is going to be L dot over R plus capital omega EZ cross ER. And we know that our setup is that ER cross E theta gives us EZ. So this is our right-handed coordinate frame. So EZ cross ER is going to give us E theta. So essentially we will have minus L double dot ER minus r times L dot over r plus capital omega whole squared e theta. Okay, so that is AQ. So we have the expression for AQ. Next we need the expression for omega dot. And we'll do the same thing. We'll do a direct differentiation of omega. So note that omega is given by this expression L dot over r plus capital omega EZ. Well, the direction EZ is not changing, it's always vertical. I mean, it is always perpendicular to the surface of the page. So the direction of EZ is not changing. So when we do omega dot, we don't need to differentiate EZ. We just need to differentiate this term, and even within there, we have L double dot divided by R. So this is essentially L double dot divided by R EZ. That is omega dot. So we have the expression for AQ, we have the expression for omega dot. Next, what we need is the expression for rho double dot R. So for that, we note that rho double dot in the rotating frame is going to be found by just taking the rho dot R and again differentiating that with respect to time, but again within the rotating reference frame. So essentially rho dot R was L dot ER, so when we differentiate, it's going to be L double dot ER. So L double dot ER, right? So we have the expression for rho double dot as well. Now, one useful observations in solving problems problems involving rotating frames is that if motion is planar, which is the case in this problem, then omega cross rho reduces to negative of the absolute value of omega squared multiplied by the vector rho. So what this means is that you take the omega vector, but take the absolute value, that is, just take the magnitude of that vector and do the square of that. So this is just a magnitude, scalar quantity, and multiply that with rho. So essentially omega cross rho is, because of this negative sign, just opposite to the vector rho. And this happens when the motion is planar. And so in planar problems involving planar motions where you have a rotating frame, this actually saves some time, because you don't then have to calculate this triple product. So we have then the acceleration of P is equal to the acceleration of Q, which is negative L double dot ER. There should not be, hold on, there should not be a dot here, so I'll just going to erase that. So this is L double dot ER minus R L dot over R plus omega whole squared E theta. So that's AQ plus omega dot cross rho. So that is going to be omega dot is given here, so plus L double dot over R EZ cross rho, and rho is nothing but LER. Okay, and then we have plus omega cross rho, and that basically will reduce to negative omega squared times rho. So we have minus, and omega, the magnitude of omega is L dot over R plus capital omega, so that square times LER. Okay, so this is the rho vector. So we have that, Then we have this term, which is the Coriolis acceleration term, which is 2 omega cross rho dot r. So plus 2 L times L dot over r plus omega. Let me see. No, this is 2, not L times, I'm sorry. So 2 times this EZ. So that's our 2 times the angular velocity cross rho dot r. Now rho dot r we see is this guy. It's this guy here. So it is L dot ER. So L dot ER. Okay. And then finally we have the rho double dot r, and that is L double dot ER. Okay. Now let us take the next step. So we have these first two terms. They are quite nicely figured out. The one thing that we can see here is you see the negative L double dot ER showing up from AQ and the plus L double dot ER showing up from rho double dot R. So these two are going to cancel. So that's helpful. And then we are going to have minus R L dot over R plus omega whole squared E theta. EZ cross ER shows up in the next term, and that is E theta. So it's going to be plus L double dot over R E theta. Okay, so another E theta term showing up. And then this guy is essentially just minus L times L dot over R plus omega whole squared ER. So that is simple. And then we have this cross product that has to be taken, EZ cross ER. And EZ cross ER is E theta. So we are going to have plus 2 L dot times L dot over R plus capital omega E theta. Right? And so now let us just combine and put all the terms together. So we have in E theta we have the following. We have 2 L dot over R plus capital omega. And you can check as you are solving these problems to see if your units are correct. So that gives just a quick sanity check. So for instance, over here you have meters per second times meters per second divided by meter. So that is meter per second square. So this is indeed, it has the units of acceleration. And this one as well, meters per second times 1 over second, so meters per second squared. So these are small checks that we can do as we are solving these problems, just to make sure that we are not totally off. And then you have the second term here, so L divided by R times L double dot. And then we have this term here, so minus R times L dot over R plus capital omega whole squared. This is in the E theta direction, and here again you can in fact check that the units are good, because let's say this guy is has units of 1 over second, so 1 over second squared with the whole squared, and R has the units of meters, so meters per second squared. We are again good with respect to the units. And in the R direction, the ER direction, we have minus L times L dot over R plus capital omega whole squared ER. So that's the acceleration of the point P. So it's a little bit of an elaborate expression, but let me just check to see if I have the right expressions here. Yep, we have the right expression. So this is the acceleration of the particle p. Right, and I would also, as we have done previously, where we, once we do a calculation, we check to see if the calculation is good or not. And one good way of verifying your calculations is to try an alternate method of solving the problem. So let me just check one thing here. Oh, sorry. So if you can find an alternate method of solving this problem, that method can, the solution through that method can serve as a check. So I would invite you to verify this solution by doing the following, at least up to the velocity level. What you can do is, you see I have drawn this I and j unit vectors. So using just this Cartesian coordinate frame, you can indicate the, or you can formulate the position of the point P, and that can be done quite easily. You see the x coordinate of point P is negative r cosine theta plus alpha, or negative r sine theta plus alpha plus L cosine theta plus alpha, and the y coordinate of the point P is r cosine theta plus alpha plus L sine theta plus alpha. Right? So let me just very quickly write this down, and as an educational and a learning tool, what you can do is you can so solve using an alternate approach. And we mention this because, of course, the goal here is to teach the various techniques of solving problems in dynamics. So an example of an alternate approach could be express the vector Cp, which is, by the way, a vector going from a fixed point C to the point P. So if I just take the derivative of that vector, I'll get the velocity, because Cp is indeed the position vector of the point P, since C is a fixed point. And you can see that Cp is given by negative r sine alpha plus theta plus L cosine alpha plus theta I, and plus r cosine alpha plus theta plus L sine alpha plus theta. That's in the j direction. And just do d dt of Cp to get the velocity. And when you get the velocity by this method, you will get it in the form of Vp is equal to Vpxi plus Vpyj. So you will get it in this form. In order to verify if you have the right answer, or if it matches with our prior velocity expression, what you can do is you can try to come up with the transform or the conversion from ij to r theta, and that can be done quite easily. If you see here, this is the j direction, this is the I direction. So j is vertical, I is horizontal. On this, if you superimpose er and e theta, the angle that r is making with respect to I is alpha plus theta, and so that same angle is being made by E theta with respect to with j, so this is also alpha plus theta. So now you can say that therefore you see I is equal to ER cosine alpha plus theta minus E theta sine alpha plus theta. That's I, because if you take ER and E theta and you resolve along the x-axis or the y-axis, this is what you'd get. Okay, so this is going to be this is going to be I expressed in terms of ER and E theta, and similarly J would be equal to ER sine of alpha plus theta plus E theta cosine of alpha plus theta. So once you have these two, you can then plug them in here and you have your velocity expressions in terms of ER and E theta. So you can try this alternate approach, and you should be able to verify that the velocity expression that we have derived using the rotating frame is indeed the right velocity. And these kind of exercises also serve as a way to improve our understanding. A student learning rotating coordinates for the first time may feel that taking this position vector and direct differentiation to be the most easiest way, and so you can pursue this approach and find the velocity. I think what you may see is that this approach of taking the position and differentiating may be a little bit cumbersome, but once you have derived it, then you can try out your rotating frame approach and make sure that the two answers are consistent, they are same, and that's also going to reinforce your understanding of rotating frames, how to formulate rotating frames, and how to solve these kind of problems. So that's it for this video. Thank you so much.